Hello everyone. In this session, we will be demonstrating some of the features and concept of ETAP power system monitoring and simulation. We will begin with a solution overview. Next, we will take a look at some of the industry challenges with the new increased visibility in power automation data. Then we will take a look at the process of the typical installation of an ETAP PSMS. Then we will explain the process of converting a traditional ETAP model to include SCADA measurements and how to convert to HMI and some of the online applications. Finally, we will cover a demo of the solution working with EcoStruxure EPAS PSO and ETAP Digital Twin Integrated Solution. ETAP Power Management Solution focuses on two core packages: Power System Monitoring and Simulation, PSMS, which focuses on leveraging the ETAP Digital Twin model to monitor and simulate, and ETAP eSCADA, which provides readily available HMIs, leveraging an existing ETAP model to generate powerful operator views. Both features can be implemented for a wide range of mission-critical industries such as generation, industrial, transportation, and low voltage. In today's industry, as new technology evolves and becomes available, there are new challenges with operating monitoring solutions. Today's power systems require to be now smarter and more effective as more data becomes available for monitoring. First, with the consolidation of data sources, today's electrical systems are now more capable than ever to monitor all real-time data from anything that affects them. Collecting data from multiple sources such as controllers, protection devices, power quality meters, and data from other SCADAs that directly affects the electrical operation and reliability of the system. Second, as more data is available, system needs to become smarter to not only monitor, but proactively validate and predict before anything happens. Systems nowadays need to be smart enough to identify any potential issues that come with electrical operation and optimization engines to identify the ideal operation. Last, system needs to be able to provide not only real-time intelligence, but also comprehensive intelligence for past events. Monitoring systems need to provide intelligence on past events to identify potential root causes for an issue and allow the user to simulate alternative scenarios in which operations can be improved. ETAP PSMS' primary objective is to meet and solve these industry challenges. One of the major advantages of working with ETAP power monitoring solution is the continuous evolution of the electrical model, allowing continuous life of the electrical model from design to operation. To begin, just like you probably heard earlier, it all starts with the ETAP Digital Twin model. As you have seen with ETAP, our power simulation software is a very powerful tool that allows you to model and simulate power systems. Depending on your industry, there is a power simulation module to model and analyze your operation, offering a wide variety of mission-critical applications such as arc flash, protection and coordination, transient stability, motor starting, just to mention a few. Now, this is where the electrical model continues its life. Now, with the model build and analyze, you can use the same model used during your design or simulation to connect to your live equipment such as protection relays, process SCADAs, power meters, just to mention a few. With the model live data, you can now increase the visibility by ETAP filling the rest of the gaps where monitoring is not available to provide you an estimation of power flows in areas where metering is not possible. Additionally, you can now start simulating the effects of changing the system, such as adding more loads, starting large motors, etc. The best part is that all of this is within the same software you just used for modeling. Then with the electrical model reading live data, you can provide powerful but very simple HMIs for your operators. These ETAP HMIs can provide key summary data for operators or management users to quickly check the status of the operation. These HMIs are built based on your ETAP model, eliminating the need for complex HMI animations and complicated navigation, all because now the HMIs are using the intelligence already built in the ETAP electrical model. And finally, HMIs allow the operation that is up to date to what is built, and engineers can use ETAP analytic engines to identify areas of improvement using powerful ETAP tools such as situational intelligence, operation trainings, etc. During the operation, as users and operators become more familiar with the electrical model and its capability, it becomes easier to identify areas of opportunity that make the electrical system more effective and smarter. Users have now at their hands their best up-to-date model, which can be used again for future studies, such as reevaluating the operation, planning, updating operation sequences with the reliable data, since now the electrical model reflects what is built and operating. So mostly everyone is familiar with how to build an electrical model with ETAP. But many of you are not familiar on how do you connect your ETAP model to start reading live data. For this, let's take a look at the very simplified way of how ETAP will communicate on a typical installation. Currently, as some of you are already familiar, your ETAP model is used to model critical electrical infrastructure on your system, such as substations. Then is also added the configuration for devices in operation. For example, the settings of protection relays that are used for protection and coordination studies. Now, to get the ETAP online, we add to the site a data collection server. These data collection servers uses the existing power infrastructure on the substation to establish direct communication to power automation devices. Our ETAP data collection server can handle many of the common communication protocols for devices such as IC6150, Modbus, DMP3, just to mention a few. Now that the ETAP model can establish communication to the devices and bring the model online, this is now where we can establish connection. ETAP will typically collect critical measurements such as power flows, voltage, current, etc., and also critical indications such as trips, changes in status, alarms, etc. At this point, engineers can now start using their digital twin model and run simulations with live data. There are some cases where maybe direct connectivity is not available to the electrical devices, or there is already an existing SCADA in place. Examples of these SCADAs are the Schneider EcoStruxure Power Automation System, EPAS, or Schneider EcoStruxure Power Operation System, PSO. In these cases, when there is a SCADA already in place and collecting data, ETAP just establishes communication to your existing SCADA to bring data into ETAP. One of the main advantages of having ETAP online is, as we showed earlier, the model can be deployed into ETAP HMIs, displaying key summary data and easy to read graphics. These graphics can be used for operations to visualize and operate the electrical system. In these cases, HMIs for operators are deployed either as a standalone or as part of the ETAP Web HMI solution. Note that the ETAP PSMS solution is hardware independent, so ETAP can communicate to different manufacturers and also different types of SCADAs as well. ETAP PSMS solution is an enterprise and scalable solution. We demonstrated earlier with a simple version of how to deploy the system. However, this solution can be scaled to fit complete enterprise solutions. The robust client-server architecture enables deployment and support for multiple clients, from clients located in dedicated workstations to secure web clients that can monitor data from the web or mobile devices. Multi-redundant systems allow continued support for an uninterrupted operation of the system in the event of a contingency. Scalable and modular design allows application servers to be deployed in separate machines for large enterprise systems. With the integration of secured managed access, administrators can restrict unauthorized login and create a secure access portals for the users to monitor their data. Support for industrial communication protocol integration allows administrators to gather data from virtually all major electrical communication protocols. This allows you to connect data from multiple sources. And just like we mentioned earlier, the entire solution is hardware independent, allowing users to choose from physical servers to virtual servers and establishing connection to enterprise systems such as SCADAs or Historias. Now that we have covered the typical infrastructure required to implement an ETAP PSMS, let's take a look from the software side. For this, let's see what does it take to enhance your typical electrical model so you can start using with ETAP PSMS. A very common question that we get when it comes to ETAP model online is, what additional software do I need? The good news, it's all within the same software. All tools necessary to get your ETAP model online is already part of the ETAP software. Therefore, no third-party tools or additional software is required. You can start building and going online using the same ETAP model to start showing real-time data on your model. In order to establish communication, we will need to define which areas of the electrical model have live measurements available. For this, ETAP includes a very powerful tool to manage monitored components on the electrical model. In ETAP, all you're required to do is indicate the areas where there are live measurements available. This is typically done by adding a component to indicate that there is a live measurement available in this portion of the one-line diagram. This could be anything from a power meter, relay, etc. In this example, I'm showing that there is a power metering available at this point. Next, all your ETAP components that will be used online are managed using a power automation database called ETAP SCADA Integrator. In this database, you can define the typical data monitored for each component. This database will help you quickly build measurements online. In this case, all I need to tell the database is what are the manufacturer device that I'm using. Then this database can create individual measurements for each device. This helps to save a significant amount of time when it comes to integration and maintenance of the system. In this demo, we can see the ETAP electrical model. This model now shows the new component for power monitoring. So in this case, I have added the components, as well as PT and CT reference for voltage and current reference as well. I will do the rest for the rest of the electrical model to identify all the points where I have a device that can provide a live measurement. As you can see from the ETAP SCADA integrator, all my components model are now listed. This effectively allows to manage model components and monitor components. Next, on the SCADA integrator tool, I will define typical measurements that I will monitor for each manufacturer device model. For example, here are the typical measurements that I will collect for my motor protection relay. So in this case, you can see that I have created all the measurements for my power measurements, as well as all my critical alarms and statuses that I will collect from this device. Then I did the same for the rest of the model. So all I need to define is the typical manufacturer device model measurements that I will collect from each device. Then you can see as I have created each manufacturer device model. So each device model is linked to an ETAP component. Since I will collect the typical same measurements from my device model, I just need to now link it easily to my model component in ETAP. As soon as the component is linked to my device model, this will automatically start creating tag measurements on my database. This will facilitate the process of building and maintaining the database. With the database built, now I have linked my ETAP model to a live component that is provided measurements on the site. So now after the database is complete, I can now go to my ETAP model and take it online. This will now collect my model and I will start receiving real-time data from my live devices. ETAP will provide additional measurements where not available and also do an electrical validation of the model. Once you're online, first, all the data that is monitored is shown in blue color. So this indicates that there is a live measurement from an electrical device. Then ETAP will add measurements to predict the power flows across the rest of the system. So in this case, we're seeing the data in red color. Second, you will be able to validate monitor data versus the electrical model. This is one of the advantages of using a model-based solution. This will bring to light any discrepancies between the as-built model versus the current operating conditions. This will also validate the quality of all measurements, but from an electrical perspective. So here we can see the ETAP, its model online, and showing my real-time information that I'm collecting from all my electrical devices. So we see all the data that is shown in blue. Now let's increase the visibility to show monitoring where there are no power meters or smart relays available. So in this case, I will go ahead and enable the new visibility. So this starts showing now. ETAP starts increasing the visibility of power flows across the rest of the system. You can see that this area is showing the estimated power flow in areas where I have measurements, but also on the areas where metering is not possible. We can also take a look at the validation tool from ETAP. With this tool, it would bring to light issues where there are deviations between my ETAP model and my online measurements. This could be very useful, particularly for cases where my actual model component doesn't match what I'm reading on my actual monitor devices. And also this could validate now all the values of measurements, but from an electrical engineering perspective. This will help to ensure that online data is always validated. In addition to the increased visibility and validation, ETAP model can be used to run predictive simulations with online data. In this feature, users can now evaluate different changes and events on the electrical system and evaluate their impact before any action or event takes place. Let's take a look at 3 common scenarios where you can use online simulation in areas of operation, planning, and switching changes. In operations, we can evaluate changes such as taking a critical circuit breaker out of service for maintenance reasons. Therefore, we need to know things like how will it affect my relay coordination. For planning, we can evaluate what is the effect of increasing the load. This could be because operations suddenly requires to increase the loads to a substation due to the changes in the process, or there is an ongoing expansion or changes in the connected loads as the substation evolves with the operations. Then we can evaluate the effects of switching changes. This could be switching from a servicing bus from A to B or taking a circuit breaker out of service. We would like to evaluate how will this impact my arc flash values. Note that all these changes we could evaluate offline. However, in this case, we can evaluate using actual operating values. This helps to review our simulation results with more confidence as we are considering the system as it's operating. With the predictive simulation running with online data, ETAP takes a live snapshot of online conditions such as circuit breaker status, operating load and generation, bus voltages, and other measurements to the analytical engine. Then users can take the online snapshot to create changes within the digital twin, and this is where users can create their scenarios for changes with online conditions and run the simulation. Finally, users can evaluate the result of the simulation and take action. This could be an answer to something like, is it safe to take this action, or will it cause instability on my system? Note that the simulations are not limited to real-time data. You can also use historical data to perform any type of predictive simulation. The process of getting real-time or historical data is very simple. With the touch of a button, we can transfer real-time or historical data into a simulation view and start creating scenarios with real-time or historical data. Now, in this example, let's evaluate a few scenarios using real-time data. First, as you can see on ETAP, we have multiple views to visualize the system. In addition to our online view, we can create multiple views or presentations to run different simulations with real-time or historical data. Let's take the case of a site that needs to bring down a critical equipment. Before the action is taken, we can simulate opening the circuit breaker and the effects on the system. Now, on the next demo, I will have side-by-side views of the ETAP real-time data showing on the left and also my simulation view showing on the right side. This will help us to take a better look at the simulation result. Here I can make the change and evaluate what will happen. After I open the circuit breaker, now I can run the simulation. As you can see, after opening the circuit breaker, this will cause one of my transformers to overload. Therefore, I must reduce my load before taking this generator offline. Another example is, in this model, there is a group of loads modeled on my ETAP model, and the current planning schedule will require to increase the load. Before taking this action, I can evaluate the scheduled amount of load on the bus, run the simulation, evaluate the results. As you can see from the scenario results, increasing this amount of load will certainly cause an overload in one of my transformers. In another scenario, we have the effects of opening a tie circuit breaker. For maintenance purposes, we want to evaluate how will this impact the system. For this, we will use transient stability and add the event of opening the tie circuit breaker at 100 milliseconds. As we run the simulation, we can see the circuit breaker open, but just after 34 seconds, one of the buses will be tripped because an overcurrent relay detecting the fault. We can also simulate other effects, such as running a switching sequence. First, in ETAP, I can build a switching sequence, then get online data from my simulator, and now I can run a scenario and evaluate each step. As we run auto start on each step, we can observe the alerts are detected as I go through each one of the steps. Using the switching sequence manager, we can evaluate for other potential issues, such as closing a ground switch without properly isolated the line. Now that we have covered the benefits of simulating real-time and historical data, we can now take a look at how do you deploy an HMI using your ETAP model. The process of creating an HMI from ETAP is very simple. Within ETAP, we have tools that allow you to convert your ETAP model to an HMI page. This is a great tool to save time building HMIs. Another major advantage is the drastic reduction on the number of animations and calculation tags required, particularly in the animations required to display the correct color for energization. By using the ETAP model, ETAP HMI engine uses the same switching device continuity coloring just like ETAP. Therefore, if an element is energized, it will also show energized on the HMI automatically. Users can also further customize symbols for electrical elements to make them more familiar for operators. For example, in this case, we can further customize the look and feel for circuit breaker and fuses to also include the switchgear enclosure, making them more familiar to the operators. In addition, custom summary views can be used for monitoring. These are particularly useful if you want to have dedicated views for specific electrical components. In this example, we can see how you can create a dedicated pop-up for a transformer and include additional critical data for the system such as phase measurements, alarm, and critical alerts for the equipment. In addition to the HMI views, there are monitoring applications as part of the PSMS solution. HMI clients can be deployed in standalone or web client for remote monitoring. Alarm and event module can further expand the system to create alarms and send notifications via email or text in the case an event is detected, such as the trip of a critical equipment or a major alarm. Custom reports can add additional operating data. For example, reports to evaluate the energy usage per operating process in an electrical system to evaluate their efficiency. Similarly, trends can be used to view changes over time of critical measurements, for example, changes in power factor over the main lines to evaluate operation efficiency. And just like we saw earlier, also the advantages of using predictive simulation to evaluate system changes. For the last section, I would like to evaluate a recent common question on implementing using an existing SCADA. In this case, we will demonstrate how does it connect directly to an EcoStructure EPAS or PSO SCADA. For existing systems that have already an existing SCADA, ETAP can read directly to the power SCADA using a variety of communication protocols. Most commonly, we use the OPC protocol to establish communications between ETAP PSMS and the EPAS or PSO power SCADA. Then ETAP PSMS server is used on ETAP digital twin clients to run predictive analysis and evaluate events that may take place on the EPAS or PSO. In this demo, I will demonstrate the PME and ETAP integrated solution. Here we can see the PME SCADA reading data directly from monitoring devices, distributed across the electrical system. These measurements are then sent directly to ETAP for analysis. In this case, we can see that once the data is brought from PME, ETAP further expands the visibility of PME by displaying estimated power flow in areas where metering is not available. We can see PME data showing in blue color, and in red color we can see ETAP calculating the power flows across the rest of the model, taking into account the electrical digital twin and the data collected by PME. In this case, we can start using ETAP predictive analysis modules. So for example, in this case, I want to evaluate what is the effect of opening this circuit breaker, get online data, and then what if it's open, then roll low flow. Now you can see all the flow through this circuit breaker are 0, where on the other side I have an alert condition. I can see from my low flow alerts that I have an opacity alert for that cable. Users can also perform many complex actions as well. Thank you everybody for your time.